All right. Oh man, we're supposed to start 4 minutes ago. I'm sorry, guys. I'll begin. Heavenly Father, we thank you for this day. I thank you for these students, this time we have to meet and study your creation. Just pray you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I hope you guys enjoyed the mission. Hopefully you have a better appreciation for like how to calculate the coordinate map and a little bit more about how we work with these abstract examples. It is an adjustment, right? It really does feel quite different than the previous course, right? Because everything in the previous course, we just do something with a matrix and we're like done, right? But now there's no matrix, right? Not yet anyway. Maybe next class there'll be a matrix. So we had last shown that the kernel and the range of a linear transformation are particular subspaces of the domain and codomain respectively, right? So what's up next is to look at linear transformations sort of on their own right and define, these hardly need definition, but let's define them anyway. So definition, if we have T, a linear transformation from V to W, and S also, S and T, both linear transformations from V to W, then T plus S and T minus S and C times T for C in the field, right? So, just to be clear, guys, we're doing what? We're working with vector spaces, V and W over a field, all right? So I won't keep saying that, but V and W are always assumed to be vector spaces in here, right? Over some field. Now, then here's the deal. T plus S of X, T minus S of X, and CT of X are equal to what? Yeah.
Do you just use the distributive property, just T times X plus S times X, and then all the way down?
Right. Now, you say distributive property, and it does look like that, but it's not that, right? What we're really defining, we're defining these new functions point-wise by these rules, right? So this is for all X in the domain, all right? So we define the addition, the subtraction, the scalar multiplication of linear transformations in this way. In fact, I don't technically need to make this definition because we already made this definition for an abstract function space, right? We said that we add functions in an abstract function space by pointwise addition. And that made sense as long as their codomain allowed addition and scalar multiplication, right? So we gave the same definitions, if you think back to the abstract, the abstract vector space F going from some set, right, S, into a vector space W, Like we defined that as a vector space back in my list of examples. And technically speaking, this is exactly that addition, all right? So to be fussy, L of VW is actually a subset of the abstract functions from V to W, right? So here's all functions. F, from V to W. They could be nonlinear, right? And this here is just the linear maps. Now, I claim that that's a vector space, right? I don't guess I actually showed you every last bit of it, but we could go through and check all the axioms for those definitions, the pointwise addition, scalar multiplication of functions. Supposing, of course, W is a vector space, that will suffice. Now there's an immediate theorem here, which is that, you know, the linear maps actually are an honest to goodness subspace of the set of all functions. And the proof of this, basically just, we use subspace test, all right? So here's the proof. Notice if we, the zero function, right? Zero map is linear, right? 0 times x equals to 0 has, for all x in V, has 0 times cx plus y equals to 0, which is c times 0 of x plus 0 of y. All right, so therefore 0 is an element of the mapping, which just sends everything to 0, is a linear transformation. And so that means that the linear maps from V to W is non-empty, right? First step in my subspace test. And then if T and S are linear transformations, right? And C is a scalar, and B is also a scalar, all right? Do you guys mind if I erase the definitions and do the rest of the proof up here, because my writing's better up here? Although now the board is wet, so we'll have a moment to talk about our day, I guess. Or I could try to dry it with this paper. It's sort of working. Oh, that would, I don't want to do that. It is rather unpleasant. So, okay, so here's the deal. If we do,
Or you can use that eraser right there.
no, we won't do that. It's like some sort of commoner. No, I wouldn't do that. I mean, come on, let's see here. So how about this? We look at CT plus S, all right? And let's let that act on BX plus Y. I'm going to try to do everything all at once, right? So we're picking up from here, all right? Now, this, by definition, is CT of BX plus Y plus S of BX plus Y, right? Then I know what? I know that S and T are linear maps by assumption, right? So I've got C times parentheses B T of X plus T of Y plus B S of X plus S of Y, right? Since T and S linear. But then this gives me B times parentheses here C CT of X plus S of X, all right, plus CT of Y plus S of Y. Fine. Look what this has come to. Look at that. I mean, come on. It's just, look at that. Just. So sad. Anyway, I still wonder where I lost my eraser shirt from earlier this semester. I don't know where it went to. It just disappeared. It's probably in my office somewhere stupid. I bet it's Daniel's fault. But look, then that is exactly, again, by the definition of addition and scalar multiplication of maps, that's B times CT plus S, right? acting on x plus ct plus s acting on y, which shows that ct plus s is an element of the linear maps from V to W, right? Because we've showed that if we can pull an arbitrary scalar out and break up a cross addition, this one calculation I've done in purple suffices to prove linearity and homogeneity, additivity and homogeneity, both axioms 1 and 2 for the linear map all at once, right? And I was super greedy. I also threw a constant in here, right? So this likewise tells me that both CT and T plus S are in this, right? So therefore subspace test, right? All right. So we have that's a subspace by the subspace test. So next up, talk about composition. And how should we compose linear maps? The same way we compose maps always, right? I don't need to really, I'm not going to define it. You already know the definition of function composition, so yay. But what we will do is prove that the composite of linear maps is linear again, right? So theorem, if let's say T is a mapping from V to W and S is a mapping from W to, let's say, U, all right, where T, of course, is a linear map from V to W and S linear map from W to U, then you guys tell me, which composition can I make? T composed with S or S composed with T? Which one is nonsense? Which one is allowed? What should I write down here? T composed with S is okay. See if I believe you. S goes from W to U. Ooh, so sorry, but no, other way around. So S, I always check it because there's a 50% chance I write it down wrong in a given day. But now that makes sense because you see, I feed T goes to W, and then S hits the W and goes to U. So this should be, according to my claim, a linear map from where? From the input of T, which is V, to the output of S, which is U. All right, so great. So proof, we look at S composed with T, and we act on Cx plus Y, right? And to be fussy, and I should be more fussy in here, after all, I will be fussy when you're not, let X and Y be in the vector space V, and C a scalar. All right, that's the preamble here. Okay, great. Definition of composite says that this is S of T of Cx plus Y. I write the reasoning over here. Definition of composite. All right, next move. T is linear. So I can rewrite that as S of Ct of X plus T of Y. T linear. Next up, I can rewrite that as C S of T of X plus S of T of Y. Why can I do that? Notice that, T of X and T of Y are elements of where? W, right? And S linear on W. Or if you like, you could just say, because S is linear, I can do this, right? More to the point. And then, finishing move here, this is c times s composed with t on x plus s composed with t on y, right? Hence, the composite of s and t is a linear transformation. And it's clear that it goes from w to u by the context here. So the composite of linear transformations is a linear transformation. The next theorem doesn't get enough love, but it should, because this theorem is like wild. So here we go. Theorem, suppose T, a linear mapping from V to W, all right, has inverse function. Inverse function S, which goes from W to V, all right? Then S is in fact a linear map from W to V. Like, this is definitely not something that's generally true for other contexts, all right? Like, to give you some sort of like, perhaps appreciation for this, in the continuous context, if you have a function as continuous, if that function's invertible, right? So you have a continuous function that has an inverse function. Does it follow that the inverse function is automatically continuous? It turns out no, there are counterexamples to this. If you have a smooth function that has an inverse, is it automatically the case that the inverse is also smooth? It's not true, actually. There are counterexamples to this. But this says if you have a linear function and it has an inverse, it has to be linear. So that's kind of neat. And the proof goes like this. So to say it's invertible means what? We have that t composed with s is equal to something, and s composed with t is equal to something else if it's invertible, right? To say the inverse function means t composed with s is the identity on where. So s goes from w to v. So this would be the identity on w, and s composed with t should be the identity on v. In other words, we have the equations t of s of x is equal to x for all x in w, and we have that s of t of, let's say, y is equal to y for all y in v, right? These things we know by assumption that the function's invertible, right? Now, let me foolishly not look at my notes and see if we can prove this from scratch. Okay, famous last words. So, what are we trying to do? We're going to assume that t is linear, right? Assume t is linear, and we want to show s is linear, right? So, assume t linear. Let's say x and y be elements of w, right? I'm going to erase this. No, I'm fine, I won't. Not the same y, obviously. All right, fine. Let x and y be elements of w and c in the field. Let's look at s of cx plus y. So what game can we play here? We could use this, right? See this? Since x and y are in w, we can replace it with t of s of x, right? Plus y is t of s of y. But then I can use the linearity of t, right? So the linearity of t allows me to pull that constant inside. And we get c s of x plus s of y. Right? But what is s of t of something? So at this way, let me go. I regret my choices. I regret my flavor choices earlier. Let me fix it so it's more amenable to you guys. If I make this a z, that may help us now to see what's going on. All right. So make that a z. Think of this as z, right? Because s of t of z is z again for all elements of v, which gives us just c s of x plus s of y, therefore s linear. Done. The next theorem that I got for you guys concerns injective linear transformations and how they behave with linear independence. So if T is injective linear map, then S linearly independent implies that T of S is linearly independent. If L goes from V to W is linear, and U, a subset of W, is linearly independent, then L inverse of U is linearly independent. In V, of course. All right. Do you see the asymmetry between these sentences? Did I assume that L is injective? I have not, right? It's enough for it to be linear. The inverse image of a linearly independent subset is automatically linearly independent under a linear map. However, the forward image, we do need injectivity, right? We do need that. Let's prove it, all right? So, and I'll keep the proofs finite dimensional for the sake of, we can, I think, I'm pretty sure this proof would still work in infinite dimensions, but I'm going to give a finite dimensional proof as to reduce the cognitive load here at the moment. So S is, V1 through V, let's say N, right, is linearly independent, subset of V, linearly independent, and T injective. All right, suppose this. Then what is T of S? What's T of S look like? T of S is literally T of V1, T of Vn, right? That's what we mean by T of S. It's the set of images of S under T. All right? Consider the sum I equals 1 to n of Ci T of Vi equals to 0. What can we do with that? What did we learn about linear transformations? How do they work together with finite sums? We can pull the sum in, right? This is the same as t of the sum I equals 1 to n of ci vi, right? Equals to 0 by linearity of t, right? But what did we learn about injectivity last class? Remember? Very good test question, by the way. The proof of this, that a linear map is 1-to-1 if and only if the kernel is 0, right? But this is a 1-to-1 map, and the kernel is 0. So this implies then that the sum I equals 1 to n of ci vi is equal to 0, as the kernel of t is equal to 0 since t is 1-to-1, right? Or injective there. I feel smarter. I said injective. Anyway. So then what? But that implies that C1 is 0 all the way out to Cn is 0. You guys tell me why. What gives me that all those coefficients are 0? What assumption? What assumption are we working under? Remember? Right here. Suppose S is linearly independent, right? As such, this trivial linear combination forces all of the coefficients to be 0, right? Right? So therefore, T of S, linearly independent. All right? So you see right where we needed to use the injectivity, right? Did you guys see why this theorem requires that? Like, how about the 0 map? Think about this. Think about this, right? If we had, like, you know, t of x is equal to 0 for all x, right? That's a linear map, right? And what's t of s then? It's just the set containing 0, right? And this is, by the way, very much not linearly independent, right? So it is crucial that our map not crush things to 0 when they ought not be, right? And if the map introduces linear dependence amongst the set, that's tantamount to there being something in the kernel, right? So we proved that last class. All right, so how about the second half of this? We suppose L linear and U linearly independent. Consider L inverse of U. What is that by definition? We're talking about x in V such that L of x is where? L of x is an element of U. That's what we mean by inverse image, right? It's the set of points in the domain which maps to the set which we're inverting, right? Okay, so consider C1 through Cn in the field and x1 through xn in the inverse image, such that the sum I equals 1 to n of ci xi is equal to 0. So what do I do? I go, okay, so if I take L of this, what do I get? L of the sum L of 0, what was L of 0? L is linear, so 0, right? 0 maps to 0 under linear map. But then again, by the linearity of L, we have the sum over I equals 1 to n of Ci L of xi is equal to 0. But this implies that C sub I is equal to 0 for all I. Since L of xi is where? We have that x1 through xn is in the inverse image of u, right? So by definition, L of xi is where? It is in u, which we assume linearly independent. Consequently, we have shown that an arbitrary linear combination of elements of the inverse image of u are once more, I mean, they satisfy the needed condition to prove linear independence of the inverse image of u. And at no point did we need to use the kernel, nothing about the kernel here, right? It's funny. The next theorem concerns surjectivity. If we have a surjective linear map, it maintains, let's get nuts. I need to start a Caesar for like washing my shirt or something. I got Caesar credit in washing the eraser shirt. As crazy as that is it so far from some of them? I don't know. All right, where was I? Suppose that the span of S is equal to V. All right, suppose the span of S is equal to V. That is to say that S is a generating set for V. If T is a linear map from V to W, and T is surjective, right? Then T of S spans W. So let me kind of give you some comments. Surjective here means that T of V is W. To say T of S spans W, we're saying the span of T of S is equal to W. All right. So proof, let's see if we can do it. Where should we start? We should suppose T is linear from V to W and onto. Also, S, also the span of S is equal to V. So in order to prove T of S spans W, I should pick an arbitrary thing in W and see if I can build it from things in T of S under linear combination, right? So let's let Y be an element of W, right? Now W is equal to T of V, hence there exists X in V such that what? T of x equals to y, right? That's the surjectivity. But what else? But x is an element of V, which is the span of S, right? Hence, there exists like C1, C2, Cn in the field, and let's say S1 through Sn in S, such that what? Such that X is the linear combination of the S's. So that means that T of X, which is y, is actually equal to T of this summation, which we can pull the constants out of and the sum out of by linearity of T, you see. But what are we looking at now? What is this thing I've just written? That's a linear combination of the image of S. Right? This is an element of span of T of S. So it follows that the span of T of S is equal to W. I mean, to be fussy, what I've shown in what I've written on the board is that W is a subset of the span, right? So to get equality there, I need to show the other direction of containment to be fussy, right? But I would argue that the other direction of the containment, namely that the span of TS is a subset of W, is immediately true from the theorems we already have proved, namely that the linear combination of vectors within a space is again within the space if it's a vector space, right? Like we already know that the span of a set is a subspace of that, and so I have this, the fact that this is a subset of W is immediate from other stuff we've already done. I don't want to. Anyway, so there you go. So a linear map takes a generating set to a generating set when? If it's an onto map, right? If it's not an onto map, all bets are off. Because if it's not onto, it could be like losing information, right? You might be missing things in the codomain. Things in the codomain you never get to, so you can't get a generating set because your mapping is just deficient. It doesn't reach the whole codomain, right? But if the mapping does reach the whole codomain, if you have a spanning set in the domain, it's automatically, the image of it's a spanning set in the codomain for an onto map again. All right. So, then I have a tour down memory lane here in terms of, standard matrices and all that. I'm going to skip that part. You guys can read it. We'll get to it when we get to it. What's up next is section 3.2, which is where I'm supposed to be today. So we're a little bit behind. Seems to be a theme for me. But here we go. So definition, if we have T, a mapping from V to W, linear map. Howdy. Well, you managed to come at exactly the most interesting part of the lecture, so congratulations. Because I think section 3.1 is full of important things to know about fundamental building blocks. Section 3.2, we start to get into the more adventurous part of the material. All right. First thing is, if that's a linear map, and U is a subset of V, then T restricted to U is a mapping from U to W defined by T restricted to U of X is simply equal to T of X for all x in u. So this is just, the restriction simply takes the given function and it throws out the domain and replaces it perhaps with a smaller one. And this is called the restriction of t to u. T sub u, like this, is restriction of t to u. All right. Proposition, and I won't prove this one because I've proved enough boring things today. If, I'm sorry, everything was interesting. I don't want to talk about. If t is a linear map from V to W, all right, and U is a subspace of V, then T restricted to U is a linear map from U to W. In other words, if we restrict a linear map to a subspace of the domain, it's still a linear map. Yes, sir?
In the definition, it says U something V, is that subset?
Subset,
or-
subset.
Subset.
Subset, yeah. Subset, yes. Now, there's a deeper theorem here, and this I use a lot. This one's actually quite important because we continue to use this, and students often find the use of this non-intuitive. So it's important to get this. But this is the theorem. There exists a unique linear extension for t. Sorry, I have to be careful. Let me write it the way I wrote it in the notes, digging myself a hole here. Suppose beta is basis for vector space, and W is vector space. All right. Furthermore, L is a mapping from beta to W is a function. All right. There exists a unique linear extension of L to V. And let me put a finer point on what I mean by that. I mean that there exists T, a mapping from V to W, such that T restricted to the basis is equal to L rather. So this is the flip side of restriction, right? The flip side of restriction is extension. So in my definition, I was talking about T restricted to U being a restriction of T. By the same token, T is an extension of the restriction. Like this T is an extension of T restricted to U. Down here, T is an extension of T restricted to the beta, which is given to us to be L. Now, let me be more precise. Like how, the theorem's more than that. It's not one of these like, pie in the sky, oh, we use the axiom of choice or Zorn's lemma or some kind of highfalutin mumbo jumbo to make this happen. No, there's just like a stone cold formula. And here's how it goes. If x is equal to the sum I equals 1 to n of ci vi, for vi in the basis, then the t I'm talking about of x is defined to be the sum I equals 1 to n of ci L of vi. this is how we create the extension. So, so the next definition then is if, t, well, let me not say t, let me say psi, or pitch for you. There we go, this guy is a mapping from V to W, is a linear bijection, then psi is an isomorphism. And we say V is isomorphic to W. Right. So I can define these linear bijections by simply defining how the basis works, all right? So if, all right, let's review the things we have today to work with, right? An injective map takes it takes a linearly independent set to a linearly independent set, right? Remember that? And a surjective map takes a spanning set to a spanning set, right? So a bijection is a one-to-one and onto map, isn't it? So this immediately gives us a theorem which is that psi of a basis must be equal to a basis, right? Because it maintains spanning and linear independence, which means that we take a linearly independent spanning set to a linearly independent spanning set if we have a linear bijection. That's an isomorphism. So this also means that the isomorphism must preserve dimension, right? If you have an isomorphism between two vector spaces, they must have the same dimension because we can take a basis to a basis, which means that they have to have the same dimension. All right? So so example 1, right? Example 1. Let beta V1 through Vn be basis for V over F, where the dimension of V is what? Apparently n, right? Phi beta of V sub I is equal to E sub I. Linearly extends to phi beta of the sum I equals 1 to n of ci vi equals to the sum I equals 1 to n of ci ei. I mean, okay, fine, guys. This was our previous definition of coordinate map, right? This is our previous definition of coordinate map, actually, believe it or not. But what this means, among other things, is that. And what I'm telling you is that once you write this down, if we use the unique extension theorem, it automatically goes down here. So if I define, right, and let's think through this. If I have two vector spaces, they have the same dimension, right? And if I can define a correspondence from one basis to another, right? Then if you believe my theorem over here, there's a unique linear extension of that. But if it's mapping to the basis, it's surjective, right? And anyway, so if you work through this, all I'm trying to say is that if we put all our ducks in a row, we'll be able to prove that if we map a basis to a basis and then linearly extend, that's automatically an isomorphism. This is how I usually build isomorphisms. But anyway, we're out of time for this week, so maybe next week. Sorry, I've spent too long on the... I was trying to go slow through the other theorem. I think it's good for you guys for me to go slow through the other